Our weather is changing. Extreme weather events are increasing. Not only is it an increase in number, but an increase in severity. We live in a time of unprecedented change, where more and more people are affected by a greater range of circumstances. We often take for granted weather forecasts like this, while many others must rely on techniques from the last century. Weather data is sourced far and wide, but it is not easy to capture data that covers an entire planet. We need a way to break through our current limitations. This is the LEMUR. Its name stands for Low Earth Multi-Use Receiver. It is equipped to capture atmospheric radio occultation profiles. Radio occultation, or RO for short, is used to measure the refraction of radio signals as they pass through the Earth's atmosphere. Capturing this data allows the measurement of atmospheric temperature, pressure, and humidity. The Washington Post compares RO as a space-based scan of the atmosphere. This makes LEMUR the latest weather scanner. These are RO profiles a LEMUR captures as they rise and set. We have more than 80 in orbit right now. Exactly how important is RO in building sophisticated weather modules? The UK Met Office has recognized RO's significance as well as Spire's positive impact across many variables. Furthermore, the Met Office, the United States Air Force, and ECMWF are integrating RO data into their numerical weather prediction models. This is a revolutionary technology with more applications being developed, including improved convective energy, also known as thunderstorm tracking, hazardous wave height radar, and soil moisture reflectometry. A greater collaboration of data leads to deeper insights. Deeper insights leads to more sophisticated prediction models, increased preparation time, response time, and more effective funding for relief aid. Not only does this data improve reactions to weather and climate change, it contributes to proactive efforts as well. Better weather prediction and more diverse weather attributes save fuel for aircraft and lowers emissions for ships. Sustainable agriculture is possible with future advances in weather prediction. Our world is changing, but our knowledge is increasing. Collaboration is the key, and Spire Global is here to help you lead the way.
Hi everyone, and welcome to Spire's first virtual weather day. Today's webinar will focus on how Spire is improving weather forecasts one satellite at a time. You'll hear directly from Spire experts in the weather forecasting and Earth observation field on how Spire's game-changing solution is revolutionizing the future of weather forecasting. And we're also going to be joined by our partners at the European Center for Medium Range Weather Forecasts and the US Air Force to discuss their experience using Spire's operational weather data and Earth observation variables. Thanks to everyone for joining today. My name is Janie Arechko, and I'm the Product Marketing Manager for the federal team here at Spire Global. And so I'm joined today by a few of my Spire colleagues, as well as our very important customers, Dr. Sean Healy from ECMWF and Dr. Mike Farah from US Air Force. And thanks to everyone for the feedback that you gave when you signed up for the webinar. Seems that we have a mix of folks who are familiar with Spire and some who are just starting to learn about us. So the presentations today will speak to both of those groups. And it seems that everyone's interested in hearing about our weather forecast information and Earth information variables, so we're going to go into detail on all of that. So now just moving into the agenda, we are going to start with a quick overview of Spire Global at a company level, and then we'll move into a keynote from Spire's recently retired Chief Science Officer, Sandy McDonald. And then we'll jump into our speaker presentations, where you'll hear from a few Spire weather experts, as well as scientists from ECMWF and US Air Force. and then we'll end with the Q&A. But remember, you can be asking your questions using the questions feature in the GoToWebinar throughout the presentation, and then we'll get to those when we get to the Q&A portion. So now I'd like to kick things over to my colleague, Keith Johnson. Keith is the VP and GM of Government Solutions for Spire. And he's going to give you a bit of background on the history of Spire and our experience supporting weather observation and forecasting, and what some of our goals are moving forward. Keith?
Great, thanks Janie, and great job. So we are so excited to have all of you on our webinar today. We have over 330 registered attendees. That's a great turnout. And so from wherever you are, good morning, good afternoon, and good evening. And thanks for joining this critical topic regarding how commercial satellite weather data can help with extreme weather forecasting and predicting. Spire has 88 satellites in low Earth orbit constellation today, collecting over 12,000 radio occultations. So you're going to hear from these experts who will discuss the quantity and quality of radio occultation and its impact on global weather models. And NOAA has stated publicly in its testing results, and I quote, based on the results of the technical evaluation of the data provided by 2 vendors in the CWDP Round 2 pilot, NOAA has concluded that commercial sector is capable of providing the quality of data needed to help support NOAA's operational weather forecasting needs. As a result, NOAA is proceeding with plans to acquire commercial RO data for operational use. Here at Spire, we believe that our recent results show that with about 12,000 radio occultations per day, there is a big improvement in as much as a half day in medium range weather predictions. A regional forecast system of 1,000 kilometers by 1,000 kilometers would have about 40 detailed temperature and moisture profiles per hour, enough for a high resolution hourly mesoscale weather prediction. So the reality is fact. More RO data makes weather models better. Fact, better models protect lives and property. And fact, commercial weather data from a LEO constellation has been tested and proven and is available today. So let's get started and hear from these experts who know a lot more about radio occultation than all of us. So I'd like to introduce our first speaker, who is Dr. Alexander Sandy McDonald. Sandy McDonald has had a 43-year career at NOAA, which included being director of NOAA's largest research laboratory and his invention of science on a sphere. He is also a past president of American Meteorological Society. He joined Spire to build our weather model 4.5 years ago, and he recently retired as our chief science officer. It has been a real pleasure to work with Sandy over the last 3 years, and his contributions have been immeasurable. So Sandy, thank you so much.
Thank you, Keith. Hello, everybody. It's a real pleasure to talk about Spire. As Keith said, after I retired from NOAA, I remembered something that happened when I was starting my professional career, and that was the incredible progress that was made when they miniaturized computers. And the revolution in satellites promises the same thing. And I'm going to say a few words how in Earth observing, we can take advantage of the incredible power that you can put in a tiny 3U satellite. I'll mention that I really see this as the third satellite revolution. When Sputnik went up in 1957, the United States was galvanized. We could see that satellites were going to make really important contributions in all aspects of our life, military, weather, commerce, whatever it is. And that has proved out beyond our wildest dreams. I always think of the second revolution as Vern Sumi and others who said, wouldn't it be valuable, he was aerospace at the time, wouldn't it be valuable to have a geostationary satellite that could continuously look at the weather? It covers about 1/3 of the Earth, and those programs, most recent one, GOES-R to GOES-16 and 17, they are an incredible part of our knowledge of the weather. But now we're embarking on the third revolution. And the third revolution really is all kinds of orbits, many orbits that you can do, a constellation with small satellites. And the simple statement is, when you have very inexpensive low Earth orbit satellites, you can look everywhere all the time. And so the miniature revolution in satellites is just going to be like the computers. We all have a supercomputer in our pocket that does everything. These little satellites are going to be the same way. Next slide. So what would a constellation look like? This is a constellation of 960 satellites, each little green dot going along a meridian. In this particular one, a typical point on Earth is in view of 10 satellites. Obviously, we're not going to start with constellations this big, but other people are. There's tens of thousands of these that people are looking at. Next slide. So let's talk a little bit why these small satellites are so valuable. And I start with highly capable. This is a picture of our lemur satellite. We actually, in my time at Spire, 4.5 years, we added panels, and we now have the power to have very high duty cycles. So the satellite itself, you can see, is sort of got antennas. We've really done most of our work with essentially listening. You know, a lot of companies like Planet and so on, they are lookers. They have an image. We listen, can be very valuable. So what can you do with a single Spire 3U satellite? Here's the exciting thing for Earth observing. We have been able to collect more than 1,000 radio occultations from a single 3U satellite. We have prospects of getting up to more, perhaps 12 or 1,400 or more. And the way we do that is we're able to collect data from the occultations from all the different constellations, Baidu and Galileo and GLONASS. There's many satellites up there generating GNSS signals, and we just intercept them as they come. We also, with this single satellite, can collect up to 1 million ship messages. We have the possibility that we could append a little weather data on that, and your knowledge of the ocean in real time increases a lot. And we all know that the importance of space weather is increasing. And the idea that these also collect total electron content and other variables for space weather is pretty valuable also. Next slide is inexpensive. We basically are integrated vertically. We actually manufacture most of it ourselves, and we can do it fast and go faster if we want to. So it's a pretty amazing piece of technology. Next slide. Here's one that people have not, I think, fully appreciated, that when you're in low Earth orbit, you actually can get a much bigger signal from Earth. So if you look here in this image, you see a little circle right by the Earth. That's the LEO, and then you've got the MEO and the GEO. So if you're 400 kilometers above the Earth and a geostationary satellite's out at 40,000 kilometers, you're 1,000 times closer. So that means a signal coming from Earth has 10,000, your signal back and forth is 10,000 times bigger signal. So it's one of the advantages when you look at the Earth, not with one little satellite, but lots of little satellites, is you get these much stronger signals. And finally, last slide, I think people are rightfully worried about what happens when some of these companies, I think Starlink is putting up tens of thousands of little satellites. Well, one of the advantages is for a satellite that's at 400 kilometers, it's only going to be up 400 to 450. It's only going to be up there 2 or 3 years, and then it'll totally burn itself up and self-dispose. So it's the satellites in higher orbit that we have to think hard about how long are they going to be up, and what are the chances of collisions or sort of cascading collisions. But it's a very important thing that we think we have solid solutions for. Next slide. So I want to talk now about Earth observing. I came to Spire because I'd spent a career in NOAA, and the ocean and the atmosphere are the most precious heritage that we have. We have to take care of our ocean and atmosphere. The dumping of 40 tons of carbon dioxide, 40 billion tons of carbon dioxide into the global atmosphere is something that has to stop. And we have to understand this planet as we deal in the 21st century with the future. Next slide. So what can we do? Well, many of you are familiar with radio occultation, but to me, it is an amazing observation. You get vertical resolution of 100 to 200 meters, much higher than microwave or infrared. You get total electron content. We've been using it, as Dallas Masters will talk about, for altimetry and looking at ice. So it's an incredible observation. We also are following on looking at NASA Cygnus and have developed our own model, or our own GNSS reflectivity satellite that, again, Dallas will talk about, where you get soil moisture and ocean winds, sea ice, and so on. And finally, there are companies such as Best here in Boulder who are looking at rain and cloud ice and water vapor. I think the water vapor one is kind of key because it allows us to separate the water vapor signal from the refractivity of the mass signal, the temperature signal. We think that the RO temperatures are so detailed and so good that the best use of microwave is to use it with these other variables. Next slide. So what can you do? Well, if you can do 1,000 radio occultations a day from a single small, inexpensive satellite, it's not inconceivable that you can put 120 of them up. We've already got 80 up, some of which are producing RO all the time and some of which aren't. You could put up 120 and get 120,000 RO per day. Why is that important? Well, as a meteorologist and somebody who's done a little modeling, if you really define the tropopause with good detail over the whole planet, it should help in your longer range forecasts. It should help with a lot, because really the atmosphere can be considered a 2-layer fluid that if you know that height of the tropopause, it really makes a difference in prediction. And I think these really detailed data that we can get from those 120,000 little red dots that I had one of our engineers plot, I think it's going to be incredible. Next slide. So here's an example of some of the work that we've looked at. If you look at the detail of the soundings, you always say, well, there's all this detail. You can see this kind of double trope and all these kinds of things. The question is it real? When you look at 2 different satellites in different orbits coming to the same point and looking, and you see a commonality, it assures you that it really is real. In this particular case, the thing that the RO is so good for, from the mid-trope to the upper stratosphere, you can see there was a big error in the GFS model of NCEP that made about a 12 millibar difference. I took a look at it, and it was just a phase error. It was just out of phase in the North Pacific. But those are the kinds of things that really make a difference when you're trying to get those predictions at longer time ranges right. Next slide. Here's an example that I love. I probably should have left Dallas to show it since he's done all the work, but we're looking here at the Amazon basin with the GNSS from Cygnus, the NASA satellite. But this is the kind of stuff that we want to do. The gray areas are where it's recently rained. And of course, the mighty Amazon is pretty beautiful. These are the kind of things, soil moisture for all the land over the earth, that are going to make an incredible difference in mesoscale weather prediction. Next slide. So a lot of the advantages, I think they come in all three time scales. I'm just going to say a little bit about short range, because that's something that we're lucky here. We have high resolution models like the HER and the NAM high resolution and so on. But I think we want to be able to do much better job in short range, because that's where a lot of the lives are lost and the most dangerous weather. Next slide. A point that I would make, looking over here on the left side, is that where do you have lots of mesoscale data? And you look at this commercial aircraft data, not just that they're flying, but also when they go up and down into airports. What you see is there's three really dense areas for data. US, part of North America, Europe, and East Asia, three dense areas. And then when you look over here in the right, you see surface weather, and you see lots of stations over the US, lots over Europe, lots over East Asia. So what you really see is this is about 7% of the Earth that have really dense data that could support a good mesoscale 1 kilometer or 3 kilometer weather model. The other 93%, the data is just not there, especially in the upper air. So if you think about 5,000, I mentioned 120,000 a day, that's 5,000 an hour. And if you get 5,000 an hour over on the right here, you're basically defining the dynamic atmosphere in a way that you need for mesoscale modeling. Next slide. I want to say that the heritage of NOAA that I'm really proud of is our satellites, our polar orbiters, and our GEOs like GOES 17. This particular image is we're doing a Spire's got us some scientists who are working on the 3D cloud structure. And so here's our Spire analysis on the left, Discover satellite on the right. You see there's a pretty good correspondence. So we don't see ourselves as doing everything. What we see is these little satellites bring a really important dimension to a fabulous science that NOAA, NASA, European Center, and the whole world has worked on for many years. This is another big positive for our community. Next slide. So we want to look at the whole Earth all the time, to have the data to run these models to improve short, medium, and long-range forecasts. And these tools that we're bringing, RO and reflectivity, I think are an incredible addition. Next slide. So I'm retired from Spire, enjoying my retirement. I think still really excited about the potential for this technology. And I think anybody that looks at it closely, you can get pretty excited too. And I thank you.
Great. Thank you, Sandy. Great presentation, and we really appreciate all the support you've given Spire. And as I said, you really helped Federal when we've been talking to the Air Force or NOAA about our capabilities. So thanks again. Our next speaker, I'm really pleased to introduce, is Dr. Sean Healy. Dr. Sean Healy is a senior scientist in the ECMWF Earth Systems Assimilation section. He joined ECMFWF in 2003 after 7 years at the Met Office. Dr. Sean Healy has worked on the applications of GNSS RO measurements since 1996, starting with the validation of GPS measurements. He designed and implemented the GNSS-RO refractivity assimilation system used operationally at the Met Office until 2010, and the bending angle assimilation system used operationally at ECMWF. He has written a two-dimensional GNSS-RO bending angle operator and has contributed to publications on NWP, climate monitoring, and reanalysis application of GNSS-RO. He co-authored a paper on the use of the assemble of data assimilation approach to estimate the scaling of GNSS-RO impact with observation numbers. So there is no question that his background and expertise is right in our wheelhouse. So thank you for your time.
Thank you, Keith. It's very kind of you. I think you can see me now. If we could go on to the next slide. So I would like to start off by acknowledging my co-authors for this presentation. In particular, Chris Burrows and Yanis Malas. Chris helps me with some of the data assimilation experiments, and Yanis was really key to us getting hold of the data in time. So I'm going to give you a user perspective of our experiences with Spire data. It's been quite an interesting period since lockdown, since the COVID-19 lockdown, and I'll give you a kind of an idea of the speed of progress that we've made in the last few months. So next slide, please. So the outline of my talk, it's quite a short talk. I'd like to initially just give you some very basic background on ECMWF. Then I'll move on to say a few words of how we use GPS-RO or GNSS-RO. I'm still working in GPS-RO. You have to get used to that at ECMWF. So when we started looking at the data, when we went operational and so on. Then I'll move on to more specifically our use of Spire data this year, and say a few words of summary and future work that we see coming up in the next year or so. So next slide, please. So the background for the European Centre. Well, we are an international organisation. We are located in Reading in the UK. We're supported by 34 member and cooperating states, employing around 360 employees from 30 different countries. We were established in 1975, and we provide both an operational service, a 24/7 operational service providing numerical weather prediction forecasts to our member states, and we also do research. And all the research essentially is guided towards future improvements of the NWP forecasts. In more recent years, we've took over operating two services for the European Union. One, the atmospheric composition monitoring, and the climate change services for the EU. So you can see we have kind of quite a broad area that we cover within ECMWF. Next slide, please. So just moving to the GPS-RO data, but I would like to kind of point out first of all that we've been a kind of a leading exponent exploiting all satellite data for NWP for a number of years, and certainly predating me. That very much leads to seeing RO within the context of the full global observing system in terms of other radiances that we're also assimilating at the same time, and so on. If you look at the kind of history books of when we first started considering radial occultation, it was work that really started with John Eyre in 1994. It's still there in an ECMWF tech memo that's on the web, where he really started to discuss how we would use and assimilate this new data type at the time within a numerical weather prediction system. And that was really based on his experience in assimilating radiance information over the previous 10 to 20 years. So he really kicked the work off in 1994. And then he moved back to the Met Office and took it with him. And I joined his team in '96. And as was said earlier, I worked on initially the assessment and the kind of CalVal of the GPS Met proof of concept mission in 1996 and 97. Fast forward a bit back to ECMWF. I joined ECMWF in 2003 on a UMS fellowship program. aimed at really kickstarting the work to get ready for operational assimilation of RO data. And I'd like to make a point, kind of a more general point at this stage, is that, you know, one of the reasons that ECMWF is able to adapt and react quite quickly to events in satellite data is we have a very strong partnership with EUMETSAT and ESA in terms of the development of forward operators, operation processing, etc. So we're usually in a pretty strong position. We have kind of quite a long-term support from these international organisations, and GPSRO or GNSSRO is no different. ECMWF started assimilating bending angle profiles operationally in December 2006, and we weren't actually the first centre to go operational with RO itself. The Met Office went in a couple of months before, but we were the first operational centre to use cosmic data at that time. So that's a bit of a history. Next slide, please. Now, the use of Spire data is quite an interesting and almost a dramatic story, really. Obviously, we've all been in lockdown, as we call it in the UK, since March, and working from home and so on. And Dr. Platzer, Peter Platzer from Spire, contacted the ECMWF Director General and EUMETSAT Director General on April 3rd, and he made an offer that he would make available the Spire GPSRO or GNSSRO profiles exceeding 5,000 per day, given that we were starting to see kind of potentially significant loss or degradation of some of major observing systems as a result of the lockdown, and specifically the aircraft was mentioned. It was decided at DG level that we would try and pursue this offer. Pretty much on that evening, April 3rd, I emailed Dallas Masters and I said, could I have a look at a couple of profiles? And I got them, and it all started from there. So if we go to the next slide, please. So we had to acknowledge the fact that we had never looked at Spire data. We had no experience with it. But you know, we had seen some very promising results, and I would say there was a very important meeting last year. There was the ROMSAF IROG meeting in Denmark in September last year, where Spire presented their results with their bending angle quality assessments. And I would say, probably more importantly, they had obviously shared this data with EUMETSAT and the Met Office, and they also reported the results about the bending angle quality. So as a result of that set of 3 talks, I was pretty clear that the quality looked, you know, certainly in the ballpark correct. And then subsequently, Neil Bowler released a technical report on some impact assessments he'd done in the Met Office and observing system, Met Office NWP system, which I read through and kind of added certain weight to the arguments. And I should say that Neil's paper is actually in QJ Early View now, so you can actually download it if you want. And also, American scientists like Ben Ruston at NRL were showing promising results. So the summary from all that information was that even though we hadn't looked at the data, we couldn't see any reason why we couldn't try to use it during kind of a short period. So that was the background for us. Next slide, please. So it was clear that we were going to have to do this very quickly, essentially. And I will, just to give you some context, we went operational with Cosmic 2 RO data in March this year, March 25th. And that followed, 6 months of this experimentation from October 19 to March 2020. And that's kind of typical for a new observing system to go in. But if we'd waited 6 months, the chances were that the data would no longer be available. So we had to make a decision, and it was decided that we would try to assess the data in a kind of compressed period of 4 to 6 weeks. We recognized at the time that we probably wouldn't get enough statistics to produce robust medium range forecast scores, but we could assess forecast improvements. We could check the data quality in a very basic level, and we could, and it sounds very coarse and basic, we could make sure that we didn't break the system. that our operational forecast system could handle this data. So we spent a lot of time, we spent this period, a really intense period, trying to sort these issues out, and really this really kind of kicked off a really an intense period of work with the Spire team, where we started a simulation experiment in April, and then with a view to go operational in early mid-May. And I would say that, you know, I'd like to comment that we developed a clearly good working relationship with the Spire GPSRO team, and any questions or issues that we had, and you always have some questions and issues with new data sources, they were always dealt with very quickly and very openly. So we had no issues in that respect whatsoever. And as a result of this, we went operational with Spire data on May 13 this year. And, you know, noting the starting point of this whole process being April the 3rd, it was a really kind of remarkable kind of pace that we did this at. Now, I can just show you a couple of 2 or 3 plots to kind of give you a flavor of the impact that we are seeing. Now, this plot, I would like you to focus on the right-hand side, please, where you see the arrow that says good. Now, what you're seeing here is the impact of the Spire data on short-range forecasts in our system. Now, what I probably should also emphasize is that the ECMWF system is already assimilating millions and millions of observations into our system. So actually demonstrating any impact in our system is usually quite a challenge. This particular plot shows how assimilating Spire data improves the short-range forecast fit to radiosonde data. So that means that gives us clear confidence that Spire data is producing a better analysis and better short-range forecasts, which are more consistent with the radiosondes that are coming 12 hours later. And this is showing you essentially the standard deviation of the radiosonde fits when Spire is assimilated, divided by the standard deviation that you would have got without Spire. And this is given as a percentage. So if you see the number 100, we don't see any impact at all. If you see a number below 100, you see a clear impact. And what you can see here is the Spire data. This is a global average. You can see the Spire data is generally on the right side, and it appears to be statistically significant from 700 hectopascals and above in this kind of temperature space. I can also show you the winds. If I go to the next slide, please. And this is the winds, the vector winds as a function of pressure levels for the short-range forecast. Again, it's globally averaged, and again, please look on the right-hand side, and you will see that the lines are well placed to the left of the 100 line, and they are statistically significant in this case from about 150 hectopascals upwards, and generally speaking on the right side below that. So that's very good. That's showing that Spire data is improving our fit to conventional temperature and wind information from radiosondes. If you go to the next slide, please. This is quite a novel plot. One of the really interesting observing systems that's got into our NWP system this year is the Aeolus Doppler Wind LiDAR. It provides line of sight winds globally. It's an ESA mission, and it's been a really big event to actually get that assimilated. It's a proof of concept mission, effectively, and it's now operational in our system. What you see here, again on the right-hand side, is when we assimilate the Spire data, we improve our fit to the Doppler Wind LiDAR winds, and that is statistically significant from about 400 hectopascal and above. So these 3 plots are really showing the short-range forecasts are on the right track, improved by Spire RO data. If we move to the next plot, this is a summary statistic that you will see quite often from NWP centres now. It's called forecast sensitivity to observation impact, and essentially it's an integrated, globally integrated measure of the quality of a 24-hour forecast, or the reduction of a 24-hour forecast error as a result of assimilating the different observing systems. And you'll see it's a busy slide, and I apologize for that. There's no other way to do this. But what you see here on the x-axis is time from January this year up to mid-June this year. And essentially, we have all the major observing systems here, and you see the orange line hopefully, is what we call GPSRO there. It should be more broadly GNSSRO. You see the aircraft plots as well. That's the light blue line. And it basically tells you what contribution your observing system is making to the reduction of the 24-hour forecast error. Again, this is, as I said, globally integrated. This is a combination of wind errors, temperature errors, and surface pressure errors. And if you go to the next slide, please, I just want to highlight some dates. If you'll notice, the orange line, the GPSRO line, has two distinct kinks. The first in March 25th. That was the operational assimilation of COSMIC 2 data. Next slide, please. And then the next kink is the operational assimilation of Spire data on May 13. And the next slide, please, just to give you a before and after kind of highlight. So you can see that we started off the year as a contribution of around about 4% of this 24-hour error reduction, around about 4%, and we ended the year around about 13–14%. And you can see that we are in the same ballpark as the infrared sounders and the microwave sounder impacting our system. So that's a really big change over the year, and it's been a really exciting year for RO as a result of both of these systems going in. So next slide, please. So I've only given you a kind of brief overview. I think the key point I want to make is that we put Spire in extremely quickly. We had a first view of the data on April 4th, and we were operational on May the 13th. That is a highly unusual situation. But I would emphasize that it was made possible because Spire had collaborations with other parties like ESA, EUMETSAT, and Met Office prior to us looking at the data. So that gave us a lot of confidence. I mean, one of the things we had heard in the past was, well, these are commercial companies, they'll only show you the good data. Now, we knew that wasn't the case because we knew that other third parties had also assessed this data at the same time. So we were fairly confident that this was as good as it was being shown by the various parties. I'd like to emphasize, second bullet down, that we worked closely with the Spire team, and all the issues we had were resolved quickly, and we have no complaints. We've had no operational issues with the Spire data since it went in on May 13, 2020. I think more generally, from my perspective, I'm an RO expert. I'm not a Spire expert as such. It's been a great year for RO as a result of both COSMIC 2 and Spire. It's probably been the best year since 2006, I would say, in terms of the excitement and just seeing us kind of making a big contribution again. So Spire's made a very important contribution to that. And then just a sentence about the ongoing work. This is kind of the wrong way around in some respects. We are currently working on an ESA study with the Met Office and EUMETSAT, and we're going to provide a more detailed analysis of the Spire data that should be useful for European decision makers in the future. So that's my talk. I hope it's I'm not employed by Spire. I'm trying to give you a kind of a user's perspective, and but it's a positive story from our side. Thank you.
Great. Thank you, Sean. And we really appreciate those words. But more importantly, we appreciate the support and partnership. As you kind of talked about, Spire, in the February timeframe, we were trying to look at how we could have a COVID crisis response. And when we saw the loss of AMDAR, TAMDAR data, as you talked about, the aircraft data, we thought that would be a good place for us to have a contribution. So we appreciate you accepting it, and we appreciate that you're doing your analysis and impact, and it was great results. So thanks again.
You're welcome. Thank you.
Okay, so moving to our next speaker is Jeff Rex, who is the VP of Engineering for Spire Weather. He's had multiple executive roles across the weather and aviation industry, most notably at Panasonic, where he led their engineering and production efforts for weather sensor development, deployment, and operation, as well as business development efforts for aviation and weather, advanced flight tracking, and satellite communications hardware and services. Jeff just joined us in the last few months, and he's made a tremendous contribution to where we're going. So thank you, and Jeff, it's all yours.
All right. Thanks, Keith. And Sean, thank you very much for the discussion. That was really interesting. And I also want to take just a moment to thank our partners, the rest of ECMWF, NOAA, NASA, the Met Office, and the U.S. Air Force, and all of our public sector partners. As I was talking with someone the other day, a couple of us were asking, well, why are we as a community in the weather business? And I think for a lot of us, the answer is similar. We of course enjoy the science, enjoy the technology, but it's to help customers, help their customers, and even society be better prepared than they otherwise would be to deal with the unpredictable and often unexpected consequences of weather. Overall, I just want to spend a few minutes with you guys today talking about how we solve business problems. In this first slide, you can kind of see how we build off of what Sean and Sandy have been talking about with radio occultation. That's really the core, is our data coming from our satellites. We take advantage of that data by folding it into our weather models. We take advantage of that data because it has a truly global reach, as you saw in the diagram Sandy showed. And then we have, a multidimensional coverage at up to very high altitudes, up to around 120 kilometers. So it gives us both a lot of breadth and depth in what we're looking at. So to the customer focus point I started with, what we're really trying to do is help our customers, businesses, organizations, enable them to have a competitive advantage. So we start by looking at things with the customers, seeing what their intelligence applications are, assessing what they are, mining with them what their problems might be, where they might have weather-related impacts to their business. And then we step into working on how we might be able to improve the accuracy of their analytics to help their business perform better. And then we'll get to a final stage where we develop a unique set of features to help customers stand apart from their competition. And so that customer focus we have right now, we're focused across primarily 4 different industries, but also across all the government efforts we've been talking about so far today. But in the verticals, we're looking a lot at maritime because it builds nicely off of our ship tracking business, our AIS business. We've been able to find that in the maritime business, there's a lot of efficiency to be gained by having better weather forecasts and better weather data globally. Aviation is kind of a similar area where you can hybridize the tracking capability, the flight planning capability, and the ability to optimize flights and reduce carbon emissions. Agriculture, really important, of course, for being able to know when to plant crops and how to phase your planning within a growing season or across multiple growing seasons that start to see patterns in the weather. And then the energy business, of course, it makes a lot of sense, especially in the renewables, where energy companies may have a solar farm or a wind farm, and they need to know more predictably in the medium range, short to medium range, when the winds are going to be high, when the sun's going to be out, because a big part of their business is their commitment to their customers of how much energy they're going to be able to provide, and they have to be able to guess that accurately, or they can be left with an overcommitment or an undercommitment, and that limits the efficiency of their operation. So moving on to the next slide, this is for those of you in the weather business, this is a pretty familiar slide. Probably it kind of shows the process for gathering weather, but one thing that's a little unique at Spire is we actually have a few extra points that are off to the left before this diagram even starts. And so initially we specify, design, and engineer the sensors we need to put on the satellites, and Dallas is going to talk a little bit about that later. Then we also manufacture our own satellites. So before we even get to the data sources, we've already specified and built and launched our satellites. And then we use the data off of those satellites, combine it with other sources of data, assimilate the data, run a weather model, perform the post-processing, and then create APIs for our customers to use. And so that, in the end, is really kind of a long value stream of how the customer can benefit from the end-to-end work we do here at Spire. So there are a couple of ways we have output available to our customers. One is what we call a single point forecast or coordinate forecast. And that might be where a ship operator or an airport or someone who has a mining operator, someone who has a specific point of interest would want to see a weather forecast repeatedly, very specific to a certain location. So you might have that at an airport for an airline or an airport operator, or maybe someone in the mining business may want to know when it's going to rain so they can prepare and get their people out and mitigate and plan ahead a little bit. At the next level, there's regional forecasting, which is a little bit bigger. It's an area of a couple hundred square miles to maybe a few thousand square miles or more. where there's a consistent area of interest for a customer's operations. And then beyond that, everything we do is based on our global forecast. And so from our global forecast is where we drill down and get these various outputs. But most importantly to us is really being able to provide visualization to our customers. And one of the ways we do that are through industry standard formats or APIs. Spire utilizes the data collected from the satellites to leverage the highly valuable global information. There are no blind spots over all the oceans and seas, as well as the polar regions. The APIs enable users to ingest climate data and match it to their precise areas of interest, which is, we think, very powerful. For instance, in the maritime business for ship owners, this means being able to align data with where vessels are located and in areas that are important to them. Another way we display the information provided to our customers is through WMS. WMS is an OGC or Open Geospatial Consortium standard format, which allows you to see different aspects of weather, different aspects of information in layers all in one display. And so it creates a format for easy integration with mapping software, for instance. It enables quick and easy integration into the visuals of a customer's internal platforms, their websites, or even their mobile applications. The power of the WMS is really in the variety that it enables in both data and styling. So the styles can vary depending on customer needs and applications. You can choose time, sequencing, weather variables, and visual styles, including things like color palettes and transparency, and then other aspects that can help with visualization of seeing multiple layers at once. So they can be tailored. And so these renderings can be done in different ways. For instance, you could have temperature or precipitation represented through color variations or contour lines, or if you like, you could have both, one overlaid over the other. Winds, for instance, could be you could have gusts in color and speed and directions via traditional wind barbs, or another customer may want something different like speed in color and gusts and contour lines. What's shown here in this graphic that's moving across the South Pacific is a 7-day period where one layer is significant wave height and the second layer is wind gusts shown in contour lines. And you can see how that would be really powerful for someone operating over the South Pacific. And what this also shows, back to what we talked about in the beginning, is the power of having data in remote areas of the world where, I should say, those are areas where it was previously considered to be data sparse areas of the world. And so now those aren't, because we have the Spire data available there. And all of this is built on a large scalable platform. So I want to also show a couple of customer case studies. Oldendorf is the first one I wanted to cover. They are one of the world's, for those who don't know, they're one of the world's largest dry bulk shipping companies, responsible for over 300 million tons of cargo capacity annually. So they're a pretty substantial shipper. Example of how significant of a game changer Spire data is, there are the thousands of soundings that aren't normally frequently sampled, but they're covering areas like the South Pacific that I just showed. They can reduce fuel consumption, reduce CO2 emission, and they can help with risk mitigation, optimization of planning, and increased operational efficiency. So going to the problem slide, the challenge that we were presented with is that Oldendorf wanted to be able to navigate more efficiently, and navigating more efficiently has multiple benefits: reduction of emissions and reduction of fuel consumption. Secondly, they wanted to be ready for the IMO 2020 requirements. And at the risk of not knowing my audience, just to be safe, IMO is not Icelandic Met Office, but it is International Maritime Organization, for those of you who aren't familiar with that industry. But basically, the IMO requirements are such that it's a significant reduction in sulfuric emissions, and it's a requirement being put in place in 2020 on shipping companies. And then on top of that, and because of that, the third thing they wanted to handle was being able to anticipate the volatility of low sulfuric fuel prices and optimize course schedules. So what was the solution we put together? We worked with our customer to first define the possible. And what I mean by that is they took it upon themselves to create a number of different scenarios where they could look at different destinations, different routing, different voyage constraints, and different models. And they put together basically a model of the possible for any given ship. And then we added in the Spire weather forecast on top of that model, and combining those two capabilities, you create a number of additional options with additional constraints based on weather. And to facilitate all of this, because all of the ships have different capabilities, different performance characteristics, a large ship, small ship, medium-sized ship, and different weights and loadings, there are all kinds of different impacts. So each type of ship was given what's called a digital twin, which is kind of like an avatar. And basically it creates a twin that runs through the simulation, and you can see how that particular type of ship was impacted by the different paths and the weather forecast that was overlaid over it, and find an optimal solution. And the next slide shows the results. The results are really kind of it's pretty amazing to me, because I worked in some different programs that were trying to save fuel and save emissions, cut down on emissions, and these numbers are pretty staggering. They saved 5.6 tons of fuel and reduced carbon dioxide emissions by 17.5 tons over a given 7-day period. So this is a pretty substantial impact when you spread that out over a year for the customer. Overall, it's an example of how, like in many industries, weather and other data are being combined with our analytics and algorithms to fundamentally change the way operations are performed and improve efficiencies. And then I have one final case study, and that's a quick one from a new agriculture customer called DigiFarms. DigiFarms is an organization in South America, and they focus on crop management. And so what they're doing is they create, they have a model that optimizes the way fungicides and other are applied in other phases of the crop management and agriculture industry are done for their customers. Weather, of course, has a huge impact. You don't want to apply when it's too wet or too dry or too windy. So the timing of having a good forecast and being able to help them with their application for their customers is really powerful. The impact that we're having with them, I think, together is that it's a quick and easy integration of climatological information with their data to show sowing dates, optimum locations, and timing feeding into their algorithms, which is really exciting. So coming back around to the beginning, our focus, of course, is on the customer, but really where that starts is kind of what we call an experience journey. Initially, today, we start talking with people and seeing what their business needs are, what their organization's needs are, how we can help them. And then we work with them to define what the key needs are that are related to the weather industry. And so the potential key needs could be things like fuel consumption or emissions minimization in other transport industries, like those we talked about in maritime. They could be something like improving container health monitoring, which straddles across a few industries, where having better weather data can help with the mitigation of condensation building up on containers. Temperature, humidity control can help with that, and ventilation can be applied based on a short-term forecast and knowing what the temperatures are going to be. But basically, wherever an organization has weather-related changes, we'd love to talk with them about it. And that's about it for me, and over to you, Keith.
Great. Thank you, Jeff. I think what's really important is the fact that Spire offers this complete solution, from the collection of raw weather data to specific use cases or applications to meet a customer's business needs. And so it's really important, as you heard from Jeff, to be able to understand what those problems are and then map them to the data and to the application. So thank you very much. Really appreciate that. Our next speaker is Dr. Mike Farrer. Mike Farrer is the Chief Scientist for Weather Operations for the U.S. Air Force. In this role, he serves as the primary science advisor to the U.S. Air Force Director of Weather and coordinates science and technology activities related to U.S. Air Force weather operations with U.S. and international partners. Mike also served from 2017 to 18 as Senior VP and Chief Operating Officer of the University of Corporation of Atmospheric Research, UCAR, and held several executive positions in NOAA from 2012 to 17. I personally like to thank you, Mike, for all your support. You guys tested us back in 17, 18, and we really appreciate that effort. And so I'll turn it to you.
Well, thank you very much. We'll get started here. So we'll break this presentation in two parts. The first part is what Keith just mentioned about the first data pilot that we did. There in 2017, as part of the National Defense Authorization Act, or NDAA. The Congress provided the DoD, and particularly the Air Force, with funds for a commercial weather data pilot. And their intent, as we understood it from the staffers that we talked to, was to really get at two issues. One was to stimulate the private sector, and secondly, to provide an alternatives to kind of the legacy way we've always done satellites, which is pretty much government run, very large satellites. Each individual satellite was very costly. And of course, the space business is dangerous. So each of them had a really, if there was a single point of failure with one of those, it could really impact all of us greatly. So we're looking at, that's what Congress had in mind. So the funds we were provided started with $5 million back in fiscal year 17 and continued on at that level all the way to now, with the exception of 1 year in 2018 where we got $10 million. And so I like to note, first of all, that next of all, that these congressional ads were for data pilots. They weren't restricted or specifically designated for data purchases. And so we have used that with that spirit in mind. We've been testing many prototypes for different data types and with different kind of usages. And so our priorities in the Air Force and DoD was to focus on the atmospheric and space weather gaps identified several years before the DoD's Joint Requirements Oversight Council. And those gaps were really talked about a term which some of you may have heard. It dealt with DoD, maybe not, which we called space-based environmental monitoring, or SBEM or SBEM. There were 11 gaps identified, things that we needed to work on to improve for DoD operations. And so as we put our solicitation out, we wanted to focus on commercial satellite options that could address some of those gaps. So next slide, please. So our first contract that was awarded for GPSRO. The prime was Astra, and they had 3 subcontractors that were data providers: Spire, obviously the subject of this call today, GeoOptics, and Planet IQ. Planet IQ at that time had not launched, so they provided proxy data only. And then Astra hired another independent subcontractor that could do some objective analyses and statistics on those 3 data types, or those 3 data providers, excuse me. And they really looked at it really in 2 areas. It's a utility and data assimilation for numerical models, which Sean Healy talked about for the ECWF, and I'll talk about next, as well as a space weather characterization. I believe that Sandy McDonald and others may have mentioned the space weather aspect of the GPSRO, not just the vertical profiles for NWP models. So that first contract was awarded back in 2018 and ended a year later. The period of performance was extended a little bit so we could finish up a few things to enable a little bit more inclusion for some of the other providers. In the end, we signed it was concluded at the end of 2019, and our final report was signed in December. And so what do we do? So there were, I say, 2 different use cases that we looked at. One was the space weather or ionospheric part. And so the way that was done is the operational Cosmic 1 data, Spire, and GeoOptics were compared with ground-based ionoson measurements. And the contractor, that integrating contractor, and their independent sub evaluator did find good agreement with all of those with the ionosons from the ground. So we were able to verify that this commercial data did a reasonable job of characterizing the ionospheric environment. We also looked at coordinate registration, and we did find that there were some of the ionospheric specifications did help us reduce errors in that as well. And then the third question, which was, does the assimilation of RO data improve the ionospheric specification? Unfortunately, those results, the way we had to do them, were not conclusive, but we did, for specifically with Spire, that the assimilation with their data did appear to perform as well as the background model itself. So it was reasonably physically consistent, but we were not able to demonstrate in that pilot project, the ability to improve ionospheric specification based on what we already had. So one important lesson learned, and we all work through this from the government and the industry side alone, is that we ran into some problems up front on format and file structure and tools and processes. We worked through all of that, and it was a useful experience, I think, for both sides of this equation. And so that was something that we did learn as we went through that. And so that was if we are able to use this data in the future, that's something that lesson learned will take forward. Next slide. On the modeling results, the assimilation in NWP models, we were able to do pretty good runs with those. In April, Spire was provided us with a little over 200,000 observations. And we were able to, our contractor was able to use the NCAR's Model Evaluation Toolkit, or MET, and other systems to evaluate. We did find that, that we were able to get improvements in our GALWIM model, which is our DoD acronym for our version of the UK Met Office's unified model. And we were able to show statistically significant, but small, but still significantly significant improvements when assimilating these RO data, which is really no surprise because we've been assimilating Cosmic 1 and other GNSS RO for a while. So we expected this. The only way this would not have worked, we don't think, is whether or not the data quality had been poor, and data quality was certainly adequate to help provide statistical significant improvements. We did show that our RMSEs were decreased, and really for the model forecast itself, our largest reduction in error was for temps, dew points, and wind speed. And we did show that the skill score for when using Spire did outperform our control beyond the 12-hour forecast. So the bottom line is that assimilating these Spire OR profiles during this pilot experiment back in 2018, 2019 did show some model improvement. And I would point out that we did not do a full data denial experiment where we withheld other data to see the relative usefulness. So this was really putting Spire data on top of all of the data we were assimilating. So given the robust data sets that are available, you saw earlier in Sean Healy's, whether it's the microwave sounders, the infrared sounders, the aircraft data, and the list goes on, adding Spire data on top of that was not expected to make a big, huge jump. So that's another lesson that we learned that we want to be able to do in the future. And I'll talk about more a little bit later, which is the ability to actually do these data denial experiments and to play lots of games with what you withhold and what you use to be able to tell really the true value. Because adding one data type on top of another mountain of data, it kind of makes it difficult to understand that. So bottom line is, next slide, let's move on. So that was the first part. The second part of the presentation, we'll talk about the live trials that have been going on the last few months. Our UCMWF colleague talked about their involvement. He did mention the Met Office was doing something similar. And for those of you that don't know, the U.S. Air Force has a strategic partnership with the Met Office. We do run their unified model as our primary global model. So we've had a long collaboration with them in other areas as well. So the fear, I'll have to repeat a little bit you heard before. We did have significant drop off in AMDAR and TAMDAR data like everybody else immediately after the lockdown in March, or starting in February and March. And we do note that we have had something like this in the past. Right after 9/11, the aircraft were pretty much shut down for quite a while over the U.S. While I don't know that we saw huge amounts of error increase or forecast skill reduction in the global model, we certainly saw it in a high resolution rapid refresh modeling over the CONUS. The bottom line was we do expect the impact for something like that to be smaller in a global model, which we have seen that. We haven't seen a huge drop off during this COVID crisis, but we have been able to show some, and I'll get to that in a moment. So as you know, it's been briefed earlier in this webinar that Spire did approach the Air Force, the Met Office, the European Center, and probably a few other folks to do this experiment, this trial run, with the spirit of the intent to try to mitigate some of the loss of the aircraft data, and of course, demonstrate the capability of Spire's offering as well. So the Met Office began assimilating this on the 22nd of May. Wouldn't you know it, get loggers involved, and it took us a while to finally get it working where we had the formal agreement where we could start assimilating it. That didn't happen until the beginning of July. So we've really only been doing it for about 5 or 6 weeks. But we are able to, because they're running essentially the same model as the Met Office, we can use some of their results as a proxy for what we would be seeing during that time. So some of the interesting statistics we saw, we mentioned the observation numbers. Of course, those are not profiles, those are multiple observations per profile. So I'll talk to you now about the number of profiles. We did find that for our observation count that we did at our 557th Weather Wing in Omaha, where we run our operational model, that we are today approximately 18 to 20,000 profiles from GNSS RO. And then the number of those profiles is roughly half Spire with the amount that they're offering, and then nearly 10,000 a day, I think, unless we're measuring it incorrectly. And the rest with Cosmic 2 and other ones, such as European sources, etc. So given that, we are nearly doubling the amount of RO profiles. You would expect the RO influence to increase, and that was seen. So we'll talk about that in the next slides. So let's move on. So this is simply the obs counts. This is provided by our 557th Weather Wing at Offutt Air Force Base in Omaha. And the dark blue at the bottom, those are the aircraft obs. So this is a stack chart, but you can see that the number of those were fairly steady right up until March, and they dropped off fairly significantly with a lot of the passenger airline service dramatically decreasing over the U.S. And you can see in the latter months it's starting to creep back up again. However, it's not really coming all that close to approaching pre-COVID levels. You'll see 2 spikes. First on the orange, midway through April there, you'll see the jump up, and that's already noted by Sean from the European Center before. That's the introduction of Cosmic 2. And then the gray at the far end in July, that is the introduction of the Spire data at our wing. As you can see, relatively, it is fairly much equaling the other observations we get. So I'm going to show you 2 different stats that you looked at a little differently. This one is in terms of energy, but it's very similar to the contribution chart you saw before. This is in data type. It's an error reduction. Typically, historically, we've seen the most profound error reductions due to satellite soundings, and that's still the same here for these global models. I will note that this is, again, a global model, so we're able to assimilate over a longer time period. I would expect these charts to look differently if we were doing hourly updating over a small window. Then the number of satellites, such as Spire's network, I think you would be able to get a much larger percentage every hour over a box for a regional box than a small number of polar orbiting satellites where these satellite sounders are. But that's something we'll get to at the end in terms of what we like to do next. But you can see the relative influence of GPS RO down the line, about a third of the way down, still very, very significant. Next slide, please. This is for May, by the way. Going to the next slide, which is similar for July. 2 things have changed here. This is instead of, let me make sure. One thing you'll notice different here is that the Met Office provided this slide. They were able to separate out the influence of Spire from the cosmic data, so you can see rather than lumping them all into one. So as you can see, the Spire about a third of the way down or halfway down there has significant error reduction and very comparable to some of the other types like the Cosmic 2. This is very similar to the chart that Sean showed. I believe the data were probably daily, so you see a lot more volatility in it. These are just line diagrams with monthly averages, so it's a bit more smooth, but you can still see some of the same features. Look to the left, about halfway up, you can see the aircraft data and it plunging down, that line plunging down into from between March and April, and it's starting to creep back up a little bit to the right. And then the other part, the line towards the bottom, which jumps dramatically up in April, May, June, and July, are the GNSS RO or GPS RO data. This was combined. This was not a separate from Spire. So this is, so you can see the original jump up in the May timeframe between April and May for when Cosmic 2 was introduced, and then it continues to rise as Spire data is brought in. And so one of the things that we didn't talk about, I don't believe Sean talked about, but I'll point out, is the relative influence of some of the satellite soundings. They do appear to drop off just a little bit. They're starting to tail off, not significantly, but I think the value there, I think you're seeing that some of that, this is speculation on my part, but I think an educated guess. I think you're seeing with the amount and the volume of with Cosmic 2 and Spire being added to this mix, that they're starting to, their influence is growing a little bit at the expense of our number one influencing observation type, which are the satellite soundings. And so this was at a certain level. There's no reason to believe, although I haven't done the experiment myself, that GNSRO line that's on an upward trend to the right wouldn't continue to go up if more soundings were brought in, especially if we're talking about a rapidly updating model, where they're coming in at times where some of the traditional data that you see at the bottom of that screen may not be available every hour. All right, so moving to the next slide. This is kind of the money slide, the summary. I want to go ahead and just recap. The bottom line is that for our commercial data project first effort, we did demonstrate there is value in this commercial data. Similarly, the live trials we've had over the last couple of months with the Met Office and assimilating the last month plus at our own Air Force office have shown positive results as expected for our global model performance. So thanks, Spire, again, for your partnership over the last couple of months as you made that data available for a trial period. So the last one I want to leave you with is food for thought, and maybe something that might generate questions. And I'd like to hear from Sean as well, assuming he's going to be on for the Q&A part. This is some of the things that has been limiting for us in the Air Force. One is that we really need to increase our testing and evaluation capabilities so we can perform on the fly more robust these FSOI or data denial experiments. We have a small staff and they're really focused on keeping the things running. And we also have a big migration from our current system in Omaha to be running our new model, our model on our new HPC system at Oak Ridge. So we're kind of bandwidth limited on some of the experiments we can run. So we really we need to up our game there for so we can really take into account these kinds of new data types in the future. Another part of it, which is really, really important, is that the business model for all of us modeling centers around the world is we have a fairly time-tested, multi-decade history of sharing data. And that's usually data that's launched by satellites launched by governments. We control the data, we own the data, we can share it with our partners. When we get into this new world, and Spire is at the forefront of this, of offering data for purchase, we don't have unlimited budgets. We're going to have to do a better job of really doing what I will say a cost-benefit analysis. It's easy to show that you add RO profiles in, your forecast ticks up in quality a bit. We need to do a better job of showing how much that's worth to us and monetizing it, because we're going to have to make a monetary decision on whether or not we can afford to buy operational data, and if so, at what level, how many profiles. So a lot of this is we haven't figured out yet, but from the government side, we need to do a better job of this cost-benefit kind of analysis, and we really only scratched the surface. Secondly, we're also looking at least in the US as a government-wide solution, the NOAA, our National Oceanic and Atmospheric Administration, has a RFP or request for proposal on the street right now for GPSRO data from commercial providers, which I'm sure our friends at Spire are busily working on their proposal to submit. Part of the options is NOAA may be able to buy data on behalf of US government partners and share it with us rather than us having to buy it separately. That's something that we have to work with on the government side. And of course, as a business, Spire has to figure out how they're going to do it on the business side. So this is kind of new for both of us. And so that's something that we're going to have to figure into our business decisions. And then finally, a little bit more detail on these FSOI or data denial experiments. We've been looking at it on a global basis, something we have not done in the Air Force at next go around. We need to be thinking about is looking at benefits on a regional basis for, let's say, high interest areas for DoD. And if we're going to run a rapid refresh version, in other words, rapidly updating similar to the HER in the US that updates hourly. We have to see the value there. I anticipate that the value of a large number of RO profiles in a regional box, I think that Keith may have been the one to talk about that as a 1,000 by 1,000 kilometer as a notional thing. I expect that if we go and do those experiments, we may be able to find that the impact there may be greater than it was on a global data set, but we'll have to do that first. We also haven't gone and done really sophisticated, meticulous data denial experiments where we have varying levels of RO profiles. You know, what do you get when you add 10,000 profiles globally for a global run versus 20 versus 30? Where is that knee in the curve on return on investment? We haven't done that yet either. That's something that we're going to have to do before we get into any kind of long-term data purchases. And finally, I think most importantly, and this is something that all of us governments, whether it's EUMETSAT launching satellites in Europe or NOAA NESDIS, which launches the satellites here in the US, is we need to do these experiments with, in the absence of some of the other data for two reasons. One, as I mentioned before, these large satellites are single points of failure. If one large JPSS satellite fails, that's a lot of data that we're depending on from one satellite. And that one satellite costs a lot to develop and put in orbit. So we need to look at what if we take away one of those and then see whether or not, or how many RO profiles does it take to make up for the loss of that, let's say, satellite sounders that are on that JPSS satellite. We haven't done that yet. I know NOAA's thinking about it, but I haven't seen any results of anything like that. That actually could influence the future. Could we offset building new multi-$100 million satellites with commercial data? I think that's really the important question to ask for the future. It's a little different now. We've already got that sunk cost and they're already in orbit producing data. But looking to the future, that's something that the US government and our partners and colleagues over in EUMETSAT for Europe probably need to be thinking about as we just decide what we're going to do for future satellites. And so I think that's it. I think I'll wrap it up there, and we get to the end, we can talk about questions. So thank you for your time.
Great, thanks, Mike. I really appreciate the insight and the food for thought. As we know, we've all been struggling with these answers, and it's kind of the crawl, walk, run approach, because we know that RO is now an acceptable weather measurement, and we know that there's a growing industrial base, and we know that more data will have additional impact, but it comes down to funding, and it comes down to where that funding comes from and the associated value that goes with that. So these are things that we're working on, and we appreciate those comments. Okay, so our next speaker is Dr. Dallas Masters. Dallas has been active in the field of remote sensing since 1995 at Los Alamos National Laboratory, where he developed the FORT satellite. He received a doctorate in aerospace engineering sciences from the University of Colorado in 2004 on soil moisture remote sensing with GNSS bistatic radar. Dallas joined Spire in 2018 to lead the development of a GNSSR mission, and he's now directs Spire's Earth observation program. His team developed Spire's EO satellite instruments and science processing systems for applications ranging from atmospheric profiling and ionosphere monitoring via radio occultation to GNSSR soil moisture mapping. Thank you, Dallas, and it's all yours.
Thanks, Guy. Can everybody hear me okay? All right. It's been an interesting set of talks today. I'm really happy to see Mike and Sean giving results from these third-party assessments. And Mike brought up some really interesting points that he made about data denial experiments, and I'll show some of those in the slides I'm going to present as well today. I think one thing that's really interesting about Spire and the satellites that we're launching and building into a constellation is the fact that we've been basically shifting the paradigm completely from relying on large satellites and moving to very capable small satellites, and in a very short period of time. Spire is only a few years old, and over those few years, it's gone from literally a Kickstarter campaign to operating the third largest constellation of satellites in the world. So with that, I'll go ahead and move to the first slide. So what makes Spire Earth observations unique? The first thing is that Spire controls the entire stack of the satellite, from the design of the payloads to the design of the bus and the manufacture of that bus. The only thing we don't do is launch those satellites. We don't own the rockets. But once those satellites are launched, we operate those satellites ourselves. We process all of the data ourselves. And this allows us to innovate very quickly. We were the first commercial producer of radio occultation data, the first operational producer of grazing angle reflections from those satellites as well. And we're still the only producer of Galileo and QZSS RO measurements in space. The other thing that sets us apart from typical CubeSat operators is that we focus on passive remote sensing using microwave signals from GNSS satellites. And this allows us to observe GNSS signals for Earth observations, as well as also investing in ship tracking with AIS signal collection, as well as ADS-B aircraft tracking. Because we control the entire stack, it allows us to iterate quickly. And this is another paradigm shifting trait of Spire compared to typical industry, satellite industry movement. We can take an idea from conception to launch and put that idea into operation in space from 6 to 12 months from conception. And we are launching satellites on the average of every 6 weeks, usually 4 to 8 satellites at a time. And that's how it allowed us to build up this third largest constellation of satellites in the world. So this is a little bit of information about the satellite. What you see on the right-hand side is the latest version of the satellite that's flying. There have been previous versions of the satellites as well. What you see in that satellite is a GNSS RO antenna kind of on the face pointing to the left. There's actually 2 of those antennas on the spacecraft, both a fore and aft facing antenna, and they're used to produce the GNSS radio occultation information that we've been discussing today. This is a 3U CubeSat, and 1U means 10 centimeter by 10 centimeter by 10 centimeter. We basically fly a stack of these in some sense in a vertical orientation, as you see. And there's 3 antennas. There's a vertical antenna or zenith antenna on the top, plus those 2 GNSSR antennas. And there are some other antennas as well that do ADS-B and AIS ship and aircraft tracking. But this is the paradigm shifting satellite that we've been flying. It's completely different than the typical satellite from the old school. We can launch many of these satellites for continuous scaling, replenishment, and improvement. So over time, we can change these satellites and improve the quality of the data that they can collect, which is something you can't do if you launch one satellite that is a $1 billion satellite. And we're doing this for long-term sustainable Earth observations to meet societal needs. It's not just a one-off mission. It's a mission that will continue to improve and continue to grow in size to meet customer demands for these types of data. The type of Earth observations that we make are using GNSS signals, and we use those signals in a number of different ways. This cartoon sort of shows how this works. We have a bunch of different GNSS satellites, and GNSS just means GPS or Galileo or GLONASS or QZSS, any of the number of global navigation satellite systems that are broadcasting these signals at L-band. And those signals are traversing different parts of the Earth environment. They traverse the ionosphere, and we make measurements of the topside ionosphere in terms of total electron content between our satellites and the GNSS satellites. We also make measurements in the lower ionosphere as well. And then the bread and butter of what Spire has been producing up to now has been neutral atmospheric measurements of temperature profiles. And that's the typical radio occultation measurement that you see depicted in the cartoon as well. As well, we now have launched GNSSR satellites or reflectometry satellites, and that's what's depicted by the word bistatic radar. And that's allowing us to look at properties of the Earth's surface like soil moisture or sea ice, as well as ocean surface winds. And that's a different type of satellite that we are moving forward with. And it's one which leverages all of the expertise that we've built in RO and now applies it to GNSSR. As well, even just having these satellites up in space and looking at their orbit determination solutions allows us to look at things like thermospheric density, something we couldn't do before without having lots of satellites in space. And there's even people who think we can measure gravity signals with these satellites because we do precise orbit determination. So these satellites and building constellations are really opening up the doors to a lot of different avenues that couldn't be explored previously. This is a depiction of sort of how we've launched a lot of satellites and grown the data volumes over time. You can see in the left plot that this is a depiction of the number of daily RO profiles that we generate. These are quality controlled, so that's why some of these numbers may be slightly different than the numbers that were shown earlier by the US Air Force and as well Sean. But these are actually quality controlled profiles, and this is over the last year. You can see how over time we've ramped up the amount of data that we can collect. And that's due to a number of things. That's due to being adaptable to observe satellites from different GNSS constellations. As I said, we're the only provider of Galileo and QGIS data, and we have the ability to do that because we own that stack and we can change that software quickly and move forward with making these types of improvements. And so as well, we just launch more satellites, and not all of the satellites that we launch are actually producing the data that you see in this plot. We actually have the capacity to produce many more data than what's shown in this plot. And the types of experiments that Mike was talking about in terms of being able to do regions of interest and collecting many data over those particular regions of interest are something that Spire could do right now. And as well, we're constantly improving the data latency for these data coming down from the satellites by expanding our ground stations and improving the way we communicate with our satellites. The plots on the right show you what it looks like to produce 10,000 profiles a day, and that was some data that we collected in February this year. And you can see it's complete global coverage, and we have the ability to fill that map in completely if we'd like to with the current satellites. And some of the statistics of the profiles that we generate are shown on the right in with respect to the ECMWF. And as you heard from Mike and Sean, the quality of the data coming from Spire satellites is comparable to the operational systems as well. And you don't have to take our word for it. And I think Sean and Mike have sort of made this point. We've engaged with our customers to let them look at our data and do the assessments on basically their terms. And we did this with a number of different partners, with the US Air Force and with the UK Met Office. And I think the UK Met Office was a very interesting impact study. We had been giving our data to the UK Met Office to do analysis of our RO data. And towards the end of that study, we did an impact study, or they did an impact study with our data. And they wrote a very good report. And one of the things about that impact study that I think is the take-home message is they did a data denial experiment. They removed METOP-C data from their normal operational assimilation, and they put the equivalent amount of data in from Spire. And they saw no discernible change, meaning, and this is what they concluded, that the two data sources were comparable quality. And so the UK Met Office was basically saying that Spire RO data were equivalent to what they were getting from METOP-C. I think that's a pretty strong statement about the quality of Spire RO data. And as well, other studies performed by NASA, as well as NOAA, the recent study that NOAA did, also concluded that the quality of the data coming from Spire was quite high, including penetration depths from our small satellites. So these are all very encouraging, and we're looking forward to engaging with more customers moving forward. And one of the things I think that I mentioned earlier about innovation is that we have the ability to change things and move quickly into new ideas. This is an example where there was speculation that these same RO signals that we are measuring in the atmosphere, if they were reflecting off of the Earth's surface, especially the sea surface or sea ice surfaces, would be coherent, and we could make an altimeter measurement that would be interesting. What I mean by interesting is comparable to the precisions that we get from $350 million satellites like the Jason's quality altimeters. So Spire went through basically a very short period of time to change software on our radio occultation satellites. And in that period of time, basically 2 months, we were able to collect these reflections off of the ocean surface. And what you see on the left is one of those examples where we have a reflection off of sea ice. And that reflection was then inverted to an altimetric height of the ice surface. And it matched very well with the mean sea surface model underneath that very thin ice to the level of less than 10 centimeter RMS error with respect to that mean sea surface model. This is unprecedented, and it's something that we basically were harnessing our radio occultation satellites for something completely different, like a sea ice measurement. And on the right, we've taken the same data and actually done a sea ice classification measurement. And so what you see are two maps. One shows the extent of sea ice measured by these radio occultation satellites, and on the right shows you a classification of those ice reflections that is highly correlated with the ice age. Now, this is taking an RO constellation and turning it into a sea ice constellation, and it just is a testament to Spire's ability to adapt and move quickly with interesting ideas and produce a very interesting new product that researchers are interested in. And as I mentioned, Spire is moving forward with GNSSR, or reflectometry. Reflectometry is the measurement of signals reflecting off of the Earth's surface, mainly for applications like soil moisture and ocean surface winds. We launched 2 of these satellites that you see on the right-hand side back in December in 2019. Those satellites are operating well, and they're moving towards full production modes and going through validation steps right now. As you see in the table, we compare these 2 small 3U CubeSats that we've launched to what are their comparable cousins, which are basically the NASA Cygnus mission. We launched 2 of these satellites. Each satellite can produce 32 reflections simultaneously, compared to Cygnus, which is limited to 4. And you can see that it's just a paradigm shift when we move to CubeSat technology like this. And as well, we're doing things that people have never tried before, like beamforming between antennas to improve the signal to noise ratio. So next slide, please. This is an example of the data coming back from one of those satellites. It's actually a depiction of an ocean reflection. And you can see in the top right, there's a map where we can see the different reflections of these GNSS signals coming from the ocean surface as well as the land surface near Australia. The blue dot shows you where this reflection came from, and it's these plots in the main plot in the middle of the screen are the reflections in what we call a delayed Doppler map. And the reason that the power that you see there is sort of spread in both delay and Doppler is the surface is rough, and it's a function of the wind speed over that surface, and that's how we retrieve ocean winds. What's different about this satellite measurement versus a Cygnus is there's 3 measurements here. There's 2 measurements from 2 different antennas, and then there's the beamformed measurement. That's the combination of those 2 that increases the signal to noise ratio, and that's also shown in the time series or the delay plot down the bottom right as well. And you can see that by moving with these interesting techniques to do beamforming, we can improve the data coming back from these satellites. And so these satellites are going to be used to do ocean surface remote sensing as well as soil moisture. And I'll discuss that on the next slide, please. So this is an example of what we're trying to do at Spire with these GNSSR satellites. These are actually real data coming from Cygnus on the left. And Cygnus, like I said, is a constellation of 8 satellites producing these types of measurements. And we've actually taken Cygnus data and used it prior to even launching our satellites to produce a soil moisture product, so that we were ready to produce validated soil moisture products from our own satellites when we launched them. And so what you see on the left is Cygnus soil moistures over a period of time, actually the entire Cygnus time series. And you can see that there are areas that are showing up wetter in blue and those that are drier in red, and they're very highly correlated with the precipitation map coming from the Australian Water Resources Landscape Model. This is the type of data that would be useful for all different types of applications where soil moisture is interesting, from NWP to initialized models, as well as agriculture and drought monitoring. And so this is a very interesting new product that we're moving forward with. Next slide, please. And lastly is space weather. And as I said earlier with the cartoon that showed our satellites are constantly measuring the electron content between our satellites and the GNSS satellites in different geometries. And we can derive electron density profiles as well as scintillation measurements from those data. As you can see on the bottom left, the amount of data that we can collect from a small constellation like this is quite a lot of data. Never before have we been able to collect these types of quantities of data, and as well as full global coverage. And so normally ionosphere measurements are ground-based measurements from GNSS receivers on land surfaces. But as you can see, Spire has the ability to measure these kind of observations in data-denied regions over the oceans and over the poles. And so some of the interesting applications will look at perturbations in the ionosphere that you see on the right-hand side, as well as scintillation monitoring. Next slide. And Spire as well is taking those same space weather measurements and not only observing them, but assimilating them into our own modeling effort. And so this is an example of what we call STEAM, the Spire Tech Assimilative Model. And we're using our measurements from our model, our satellites, and assimilating them into this model to produce near real-time forecasts, or near real-time nowcasts of the tech environment, as well as extending this model to actually be able to do forecasts as well. So we're taking the data from our satellites and we're actually moving it into an area where we can produce products that are useful to the community for space weather monitoring. Next slide, please. So finally, just a few key takeaways. Spire's built the world's third largest constellation of satellites, mainly for Earth observation. We're currently at 88 satellites with a dozen satellites sitting on rockets right now ready to be launched to add to that constellation. And these satellites are enabling new Earth science and applications that never before have been possible without a constellation of satellites. We're now expanding into more space weather science after actually proving that we can do this with commercial RO. We're now moving into space weather as well as GNSSR applications. And we consider other Earth observation payloads as well. There's actually space still available in that 3D CubeSat, if you can believe it, to put more interesting payloads. And the amount of data that we can collect and the coverage and temporal sampling of those data is what makes this a very interesting and paradigm shifting technology. These satellites are cost effective in terms of launching them. As Mike said, when you lose $1 billion satellite, you lose a large chunk of data. With Spire's idea to replenish these small satellites and launch many of them, the system is much more resilient than the typical old school paradigm. And Spire sees itself as producing these satellites and these data sets for continuous scaling, replenishment, and improvement, basically for sustained long-term Earth observations. I like to say that from now on, graduate students are going to be trained not just to work on the one satellite that might die within their graduate career, but now they're going to be working on data that they can expect to be there when they graduate and continue to work on those data for their entire career. Because we expect these satellites and these constellations to continue to be replenished and to continue to be producing impactful measurements for the future. So with that, I'll turn it back over to Keith.
Great, thank you, Dallas. Really appreciate your comments. And if you think about it, Spire has the ability to offer a total solution. It's available now, it's tested and proven, and RO, it has an impact. So that's kind of what we've heard consistently. So in closing, I want to thank the speakers. In appreciation of your support and your words, I'd like to send each of you a Spire polo shirt. I will talk to you offline about that applicability and sizes and so forth. But thank you so much. And I will give it to Janie now.
Great, thanks, Keith. And I just want to reiterate, thanks again to all the speakers for taking the time and effort to present to us today. Some great information, we really appreciate it. So we're about to move into the Q&A. So the question is, will the slides and the recording be available after the presentation? So the answer is yes. We'll be sending those out, both the slides and the recording. So no worries on that. All right, and we have a question here for Sandy. So Sandy, can you tell us, how do radio occultation soundings compare to microwave and infrared soundings?
The radio occultation has a higher vertical resolution, and I think that makes quite a bit of difference when you know exactly where the tropopause or the top of the boundary layer or layers in the stratosphere, which are actually vertically propagating gravity waves. That helps a lot. So the high vertical resolution of radio occultation, I think, make them a really important data set, especially if you get very large numbers in the future.
Great, thanks, Sandy. We have a question for Sean, if you're still there and available. The question here is if you could talk about the impact of Spire and Cosmic 2 data below 200 HPA, where we really want to know how the signal to noise ratio will make better moisture. better moisture readings, I think, and help NWP through DA. I'm hoping you know what DA is there.
Yeah, I can probably.
Great.
So I think what we're saying, what the question is here is the Cosmic 2 instrument has a higher signal to noise, so it tends to have a better quality bending angles in the kind of lower troposphere. And we have just started experiments for ESA, where we will be comparing the impact of Cosmic 2 and Spire and the combined impact for the January to March period. My impression at the moment is that you do squeeze out more humidity information from Cosmic 2 measurements than Spire measurements as a result of the signal to noise. But that is work to be continued.
Great, thank you. Mike, I think we have a question here for you. And the question is, does your office share this type of data with the other services? So to be specific, are your assessments shared with the Army and other DoD and Intel offices?
Yeah, we did share the final report of our original data pilot. So anything that we can share and protect, if it's proprietary, we can share it amongst our government partners. So there's some things that if there's proprietary information, we can't publicly share it because of the proprietary nature. But for the most part, we don't broadcast it because there's just too much going on. But certainly the partners that we've worked with, such as Naval Research Lab and the Army, have received some of our information when requested.
Great, thanks, Mike. So then I have a question here. Probably a few of us can answer, but I'll throw it to Jeff. Can you provide any technical information on the Spire weather forecast model? So the domain, is it a global model? What's the spatial resolution? What forecast period do we offer? So some of those specifics.
Yeah, sure. It's a right now we run a forecast out to 7 days. We run it twice a day at 12-kilometer resolution or a G8 resolution, depending on which characterization you use. We also run a statistical model for short-range forecasting that we run out to 24 hourly, out to 24 hours.
Perfect. And I think we have, a lot more information on our weather forecast. We can always share that, and send over to you if you're interested in hearing more of the details. So we have an interesting question here. I think Dallas, you might be able to answer this. So the question is that, current radio occultation right now is done satellite to satellite. Could something similar be done using ships at sea? So could we put a receiver on a ship that has a clear view to space and observe GNSS satellites and collect data? And then could we transmit that data to our satellites? Is something like that possible?
That's an interesting question. That's somewhat similar to a ground-based GNSS measurement, like what we normally would do with receivers that are part of geodetic networks. And yes, those receivers can make measurements of tropospheric water vapor, and you can do tomography with those types of measurements. So those are potential applications that could be pursued. Spire, of course, obviously is very much focused on satellite measurements because they do give us that global coverage. But there are definitely some interesting avenues where measurements on ships could be transmitted. And in fact, Spire's AIS system could be used to get all of those measurements in a very timely manner to be assimilated as well into weather forecast models.
Great, thank you. Another question for you, Dallas, I think you're probably best to answer. So the asker says that this EO and GNSS RO data would be great benefit to the academic research community, but there's of course a concern about cost barriers for the cost of commercial data. So is there anything that we're doing to help the research community and help make that data more available for them to use in some of their work?
Sure, that's a good question. We trial our data with researchers, constantly asked questions about our data, and we try to get the data into researchers' hands for trials. But then we also are actively working with NASA and ESA, and specifically NASA. I want to highlight that program. We just recently signed a contract with NASA to deliver 6 months of historical Earth observations data to NASA, as well as the next 12 months of Earth observations data to NASA. And this includes the entire variety of data that I showed today, from radio occultation measurements to the precise orbit determination measurements that could be used for really interesting research like thermospheric density and gravity measurements, as well as the GNSSR and the grazing angle measurements. So that's a very interesting way for Spire to leverage NASA's expertise in working with their researchers. And I encourage all researchers to reach out to NASA to find out how to do that. And as well, ESA is moving in the same lines, and we have a small program starting with ESA that will also bring data to ESA researchers. And I hope that that program will grow in the future as well, so that many more researchers will get their hands on Spire data, and they'll be able to actually look at some of these applications that a constellation of this size is actually making possible now.
Great, thanks, Dallas. We have a fairly straightforward question here, I think, likely for Sean or for Mike, given the some of the graphs and calculations you were showing. Someone wanted to know how the error correction is calculated.
Right. That is quite a seminar on its own, actually, to be honest.
Okay.
This is some work that goes back to NRL researchers, Nancy Baker and Langland. And it's all to do with using the adjoint of your forecast system to look to see how, if you'd lost the data 24 hours beforehand, the error would have increased. Short of saying that, I can point them to the papers, but there's no way I can do that verbally. Otherwise, I think it'll take some time. Sorry about that. But
Okay.
it is a standard metric that you'll see in most NWP centers now, that people do it this way. Now, not everybody likes it, and you know, but it seems a quicker way of kind of assessing the kind of different observing systems relative to doing OSSEs, which is very much more expensive. But I don't know if Mike can kind of flesh that out at all, but it's quite mathematical to actually show how to do it.
Well, you've already exceeded my knowledge of how that's calculated, Sean. So I'm not have a lot to add, but I'll just foot stomp the point about the cost of the Aussies. You know, this adjoint-based method can be done in real time and just be calculated as the model's running. It doesn't require you to rerun the model and withhold data, and that's where the cost comes in. To really do this in a brute force way, you'd literally have to run the model in every configuration possible, with withholding one data type and two data. So to be able to determine the absolute influence of one data type is very difficult. So this method is by far the most convenient way, and it does provide value. And you can see just from the trend analysis that came up, regardless of the actual absolute value, the trend analysis, you know, is very, very reasonable. You can see the increasing influence of the RO data as more profiles are added, the decreasing influence of the aircraft data as those are extracted. So you can tell that it is working, but it is, as Sean said, it's a seminar in and of itself, and I can't add anything more on top of that.
If we get the email, we can certainly point to the relevant papers. I think is probably the best thing, and discuss it beyond this meeting.
Great, thanks both of you. We can definitely connect you with the question asker. So I think we're running up on time, but I think we'll end on this last question for Jeff. So for Jeff, have there been any recent third-party evaluations of Spire data with respect to weather forecasting scale? Obviously, we looked a lot at radio occultation and that impact, but any way that we're comparing kind of our own weather forecast?
Yeah, so third-party evaluations, there have been a couple of recent ones. One of the most recent is one performed by NASA, which was in a paper called Commercial Smallsat Data Acquisition Program Evaluation Report, and that was just in April. And then just before that, I think there was one that Dallas may have also cited, which was from the Met Office in the UK, which was the assessment of GNSS RO data produced by Spire. That was in February, and it cited a substantial forecast benefit from assimilating Spire's data. And so that gives us a little bit of third-party validation on improvement of our forecasting capability. Of course, internally, we work to optimize and tune our models so that we take the maximum advantage of our own data.
Great, thanks, Jeff.
Could I add something there,
Oh, absolutely.
Jenny?
Yeah.
Just to kind of publicize my colleagues, I mean, Neil Bowler's paper on the Spire impact has been published in Quarterly Journal, and it's available on early view now. So if you are interested, it is available from the Quarterly Journal web pages.
Yeah, that's great. Good point. Thanks, Sean. Appreciate it.
Great. So I think we're going to wrap up. We're hitting up on time here, but if there are any other questions, we have the list of questions that you sent. So if we didn't get to yours, we will follow up with you via email. As well, if you have any other questions for us or you want to reach out, this is our contact information. Please, we'd love to hear from you. And specifically, if you're interested in trialing Spire data, Ashley O'Neill is the person to talk to about that. So her email's down there in the bottom right. And I just wanted to thank everyone again for joining today. Some great presentations. Thank you to all the speakers. And thank you to everyone for asking your questions. We really appreciate you joining us on the webinar today. So everyone, stay safe and stay healthy and have a great day.